It's a pleasure to be part of this very interesting conference. Unfortunately, I think that the intersection between what I'm explaining here and what I heard in this day is not totally empty, but is small. And because of that, I decided to have a talk which is not at all technical. I would like to explain what is my feeling of investigation, what I did in the last year, but on a simple level, and just to try to convey something that maybe could be of some interest for us. Then I apologize for the one who prefer a hard math talk. This will not be of this type. There is some intersection, and the first intersection, I think it's the word algebra. I heard a lot of algebra here. I work with algebras. My algebras are sister algebras. And then let me start a little bit recalling this definition. What is a sister algebra? Essentially, a sister algebra is an algebra over the fields of the complex number. There is an antilinear involution, an adjoint. This is the star which is in star. There is a norm. Then it's complete with respect to this norm. And the norm is, the product is continuous with respect to the norm. This means that this algebra indeed is a Banach algebra, and because of the star is a star Banach algebra. But the C in the name comes from these properties. These properties, it looks quite trivial, but indeed it's a very deep properties. This is called the C star property of the norm. And because of that, topology and algebraic structure of this object are intertwined in some sense. We can recover the topological property from purely algebraic property of this object. Okay, I don't want to enter in this question, but these make topology and algebraic structure essentially the same. Which are the main examples? There are two examples. The first one are the continuous function over a locally compact Hausdorff space. Okay. And the second examples are sub-algebra of the bounded operator and an Hilbert space. And these are not just two examples. In some sense, these are the canonical examples. There are two main theorems in this theory which tell us that commutative sister algebra are indeed of this type, and the non-commutative sister algebra can be always reduced to algebra of this type.
The second example, we mean the operator norm.
In this case is the operator norm, in this case is the norm of the supremum. Okay? Well, if I have an abstract object, a sister algebra is an abstract object, then I want to have representation. A representation is a star homomorphism of the algebra inside bounded operator of some Hilbert space. This is called a representation on H. And automatically, this just follows from various definitions, the representations are continuous, in some sense decrease the norm. And indeed, the representation is faithful, or it's an isomorphism, when it is injective, when it preserves the norm. Okay? Well, another notion that I will use in this talk is the notion of the spectrum. The resolvent of an element of the sister algebra is the set of points of the complex plane such that A minus lambda is invertible inside the algebra. And the spectrum is just the complement of the resolvent. Now, let me point out that this definition is purely algebraic. Okay, I don't need any Hilbert structure. I don't need a C-star structure. Just a star algebra. Just in a Banach context, this works. Okay. I stress this point because this is the second part. When pi is a faithful representation, then the spectrum, the algebraic spectrum, coincides with the spectrum of the operator in the Hilbert space. Okay? Then what I mean that we have a way to compute spectrum of some operator without looking at the representation just from the algebraic context, if I know that the representation, for instance, is faithful. Well, I'm introducing sister algebra because in particular I'm interested in one particular sister algebra. This is one of the canonical examples of non-trivial, non-commutative sister algebra. I need few ingredients to create this sister algebra. The first one is a parameter, is a real parameter. It's called the deformation parameter. I think the name, it will be self-evident why deformation. And then I need two abstract unitaries operators such that the inverse coincide with the adjoint. And I need a commutation relation between these two elements. In this case, you know, the deformation parameter is just the quantity that tell me that these two objects does not commute. They commute up to a phase. Okay? Then we are deforming commutation relation between commutative operator and in some sense forcing some non-commutativity in this structure. And then what I can do? I can construct polynomial in U and V. And these polynomial indeed are well defined because, you know, I can always decide an order. For instance, to put the power of U on the left and the power of V on the right. And because of this relation, I can always order my polynomial. Then the definition of polynomial, it's, in some sense, it's natural. And the polynomial are a star algebra. I can sum polynomial, I can multiply polynomial. I have, because of this condition, I can define the adjoint on the polynomial. What I need is a norm. Now, there is a canonical way to define a sister, not only a norm, I need a sister norm, okay? And I repeat, a sister norm is a norm which met the sister condition. The norm of A star has to be equal to the square of the norm. And there is a canonical way to endow an object of this type with a sister norm. This is called the enveloping norm of the universal norm. I'm looking at all possible representation of this star algebra inside Hilbert space. I can compute the norm of the representation in the Hilbert space H of the element A. I can compute the supremum over all the possible representation, and I declare this the norm of A. Okay? This procedure is quite abstract, but it works, at least for abstract nonsense. This defines a norm. And what I can do, I can close this star algebra with respect to this norm, and the final object is a sister algebra. Okay? This sister algebra in the business of non-commutative geometry is called noncommutative torus. And well, the reasons are quite evident. Let me, well, just let me say why. Okay, imagine to work on a two-dimensional torus, and you can construct the polynomial over the torus just as a polynomial of the two exponential which generate the continuous function over this torus. Okay, I can essentially write any continuous function over the torus as a Fourier series. And the two exponential indeed are unitaries in the algebra of the continuous function over the torus, and they commute, in this case, theta equals 0. In some sense, what I'm saying that when theta is equal 0 is any integer number, the algebra that I'm constructing here is just the algebra of continuous function over the torus. Okay? When theta is not an integer, is still a torus, but is non-commutative. Okay? We cannot represent this as a space, but we still have an algebra of, in quotation mark, function. Well, and because indeed this is a torus, in a torus I have a calculus. I can extend my calculus to this non-commutative object. What I can do, I can integrate. I can define a trace on this sister algebra just by this prescription. The trace of this monomial is 0, but the case when this monomial coincides with the identity. And then I can extend this prescription by linearity to polynomial, and then to hold the algebra by continuity. And indeed, if you think at the example of the function of the torus, I'm just saying that the integral of the exponential are 0. They integrate to 0. And the integral of the constant function, the identity, is just the volume of the torus that for me is normalized. Then, because I have a trace, I have a non-commutative integration theory. For instance, I can define the LP space of this algebra, okay? As you can usually do with the ordinary measure theory. I have also a notion of derivation. I can derive function. And again, I define this derivation on this monomial. In this case, I'm doing the derivative with respect to the first coordinate. In this case, with respect to the second coordinate. If you think at the example of the torus, an object of this type is the power n of the exponential in the first coordinate. And when I derive, I just get an n here. Well, this is the phase. Well, there is a mistake here. I miss an I. Sorry. And because I have this derivation, I can, for instance, define what are smooth functions. Smooth element of my algebra are elements which support all these derivatives. These derivatives are unbounded, are not defined on all the elements of the algebra, but this is not well. We know that there are continuous functions which cannot be derived. Okay, it's the same things here. Well, I can also define Sobolev space, non-commutative Sobolev space, are space in which I'm asking regularity with respect to the derivative and LP properties. I will not use this question here, but just to tell you that with this non-commutative object, indeed, we can really have a calculus, a complete calculus. Well, another important piece of the theory is that these objects indeed are topological objects, in the sense that, for instance, I can consider projection. Projection are elements, self-adjoint elements, such that the square of P is equal P. And the set of the projection on a sister algebra, in some sense, is representing the disconnected component of my space. What I mean? Look at the canonical example, a sister algebra of continuous function over a space. If this space is connected, the only way that I have to construct, the only way in which I can construct a projection is O, the identity function, which is identical 1, the constant function 1, or the constant function 0. The constant function 1 is the identity of this algebra, and 0 is the trivial element, and I have no other projection. If my space is disconnected as two disconnected components, then I can construct the function which is 1 on one component and 0 on the other, and this is a projection. Okay, then the family of projection in the commutative world, in some sense, is related to disconnected component of my space. In the case of the torus, for instance, when the parameter theta is 0, because the torus is a connected manifold, in this case I have just the trivial projection 0 and the identity 1. But what is interesting is that in the non-commutative case, the non-commutative torus usually has a family, a non-trivial family of projection. Then it is a non-commutative torus, and it is highly disconnected. This is interesting. And this projection will play a role in what I will tell here. I can do a little bit more. This is a trivial topology, but I can do something which is a little bit more sophisticated. I can construct K-theories of this algebra. I don't know if you are and how expert are you on K-theory, but essentially the way in which people in non-commutative geometry construct K-theory is this. You take the projection, you tensorize the projection with the compact operator. This procedure is called the stabilization. And then I define a notion of isomorphism of stabilized projection, which essentially is to homotopically deform one projection in another projection. And the equivalence classes of this stabilized projection modulo this equivalence indeed is a semi-ring, is a semigroup. And if I have a semigroup, I can construct a group with the Grothendieck procedure. Okay? essentially this is the same way in which I can construct the integer starting from the natural number. Okay? This is the Grothendieck trick. And this is a group. This group describes the topology of essentially my non-commutative space. In the case of a commutative space, the K-theory, the K0 is just the classification of all the possible vector bundle over my space, modulo stable isomorphism. Okay? Then indeed this group is describing the non-commutative vector bundle that I can construct over my space. And okay, in this case I can compute this group essentially is a Z plus Z. There is a theta because, you know, this group indeed has a little bit of more structure. It's not only a group, it's a ring. You can define a ring structure. And the way in which I can associate these two numbers to any projection in this group is the second element, this M, which take values in this theta Z. I will be a little bit more precise afterward, is just calculating the integral of the projection P. And this defines in some sense the rank of my non-commutative vector bundle. And the second element which classifies the projection is the Chern class. Because I have an integral, I have a derivative, I can construct a non-commutative curvature, I can integrate a non-commutative curvature, and then I have an integer. Okay, this integer is called the Chern class of my projection. The fact that this number is an integer is not trivial, it's a theorem. Okay? Well, now, I finish my classes in sister algebra, and then I can switch to butterfly. What is a butterfly, at least in my definition? Well, essentially, I already say many of these things. Okay, I repeat, when theta is an integer, the non-commutative torus is just a commutative torus. Clearly, from the definition of the twisting of the deformation parameter, if I change u with v, if I do this morphism of the algebra, then this is the same to go from theta to 1 minus theta, and then it means that the algebra A theta, the algebra A1 minus theta are isomorphic. And then, in some sense, these results tell us that all the possible non-isomorphic realization of the non-commutative torus are parameterized by theta between 0 and 1 over 2. There is another result that, in some sense, I will use in this talk. When theta is a rational number, then this algebra indeed is just an algebra of function over the two torus with values in the n by n matrices. Okay? This algebra can be represented as a function over the torus, continuous function over the torus with the value in the n by n matrices. In some sense, this tells us that there is a Morita equivalence between this non-commutative algebra and the commutative algebra of the two torus. And okay, when theta is an irrational number, this algebra is called the irrational rotation algebra. And for many reasons, the irrational case is the, let me say, the interesting case. It's the interesting case in the sense that it's the case in which this algebra is really deeply non-commutative, okay? Because when theta is rational, this is a non-commutative algebra, and the commutative is just in the matricial part. Here, it's intrinsically non-commutative, okay? I don't want to insist too much on this difference. But this dichotomy will be evident in some of the pictures that I will show you. Okay, now, what I can do? I can choose a set of coefficients, and I can construct a formal polynomial of this type. And I can pick u and v on some realization theta of this algebra. But if these coefficients are fixed, I'm defining in this way element of the algebra a theta. And you know, this element, it depends on theta. What I mean, that choosing a, u, and v on different a theta, I'm having a family of elements which are parameterized by theta. And let me consider the map which associate, well, I fix f, the functional form of f, in the sense I'm fixing these coefficients. Then to h theta, I can compute the spectrum of f theta. This is inside the compact set of R. Okay, then this map is well defined because I have the notion of spectrum on my sister algebra. Of course, the reality here is implied by the fact that f is a self-adjoint. Then if these coefficients are such that this expression is self-adjoint, I have this map. And then I define the butterfly associated to the operator f. The butterfly associated to this family of operator f is just this joint union of all the spectra of f theta when theta goes from 0 and 1. Okay? This is my formal definition of quantum butterfly for the family of operator f. And look, this is the most famous of this butterfly. This is called the Hofstadter butterfly. This is the family of all the spectra of operator of this type. You know, it's the simplest self-adjoint polynomial which contain u and v. Okay. How I have to read this picture? I fix a value of theta, for instance, in this case 1 over 3, and the spectrum is here on the vertical part. For instance, the spectrum of h theta for the value theta 1 over 3 is made by this 3 band. At 1/2, the spectrum is just one central band, but it's morally given by 2 bands which touch in the center. And you know, this picture is it's interesting. It's immediate to recognize that there is some structure. Indeed, it's a fractal. And you know, you can imagine the spectrum at a rational point as a limit of this spectrum for rational point. And one of the main results in the study of this picture is that for irrational point, the spectrum of this object is usually Cantorian, are Cantor set.
What about the multiplicity? Is it always line?
Multiplicity of what? Of
The point is
for rational, the spectrum is absolutely continuous. Okay, and then there is no multiplicity in this sense. It's absolutely continuous. You have a absolutely continuous density in the spectral measure. And for the limit case, in the rational case, it should be, I think, of multiplicity 1. I'm not completely sure, but it should be in this way. Well, this is called the Hofstadter butterfly because this picture was the result of the PhD thesis of Douglas Hofstadter. He was the first able to program a machine, and I think after a week he went back to the office and this butterfly popped up, and he was extremely fascinated by the, let me say, the beautiness of this picture. And indeed, this is, I think it's quite correct to say that this is the only contribution to mathematical physics that he gave, because then decided to change completely. And you know, today Hofstadter is a big guy in computer science and stuff like that. Probably the beautiness of the butterfly was somehow inspiring for him. But you know, this is not the only butterfly. Essentially, we have a butterfly for any element of our sister algebra. There are other examples which are considered in the literature. This is called the triangular lattice butterfly. The name, I think, I hope, will be clarified in in the next part of my talk. This is the spectrum of the Hofstadter element plus lambda this perturbation. And you know, in this case, the butterfly looks like a little bit deformed. The meaning is always the same for each rational number. The spectrum is on the vertical part. For instance, it's possible to study the transition between the triangular and the Hofstadter. The Hofstadter is the square lattice butterfly. When the parameter lambda goes to 0, this is the evolution of the butterfly. You can see that maybe going from this way to this way, there are singularities, okay? Here, the spectrum change in a singular way from year to year. The gap structure change. Then these are the type of argument that people studies in this business. There is another nice butterfly, which is the honeycomb lattice butterfly. In this case, to realize this operator, you have to tensorize the noncommutative torus with a 2x2 matrices. Honeycomb because it's related to an honeycomb lattice structure in some sense. This is related with the graphene physics, this spectral diagram. And what I want to do now is to go a little bit beyond the spectral description. I want to add some more information to this butterfly. This more information are in some sense the color. I want to color this butterfly because you know, white and black butterfly are not so interesting. Because of that, I need to introduce some few objects. And you know, for rational number, we have seen in this example that the spectrum is made by bands and gap usually. Okay, then just let me label this band with the A1, A2, A and 0 minus 1, A and 0. And because there are gaps to each one of these intervals, I can associate a projection. How can I construct this projection? Well, I have the Ritz formula. I can choose in the complex plane a closed path. And essentially, I can use the Cauchy formula for the holomorphic function. I don't know if you, well, let me, the projection Pj, it's 1 over e 2 pi, the integral over the circle of, well, this is for the function f. In this case, I have to write f minus z minus 1 in this z. Okay? This formula makes perfectly sense in the context of any Banach algebra. Okay, my function can be function in Banach algebra, and I can use this formula. Okay, this defines a projection. This projection, by construction, is inside the sister algebra. Okay, then to each energy band, I can associate a projection which is in my sister algebra, and yes, essentially, this is the way. There is another result, because for this rational parameter, I know that my sister algebra is made by continuous function of with value into n by n matrices. The number of this band cannot be bigger than n, okay? The denominator of this parameter, theta. Okay, and then it means that I can label this energy band with a number which goes from 1 to n0, and where n0 is not bigger than n, which is the denominator of this parameter. And I'm not interested in labeling the energy band. I'm more interested in labeling the gaps, and I can just labeling the gap k. Just summing, define a bigger projection, which is the orthogonal sum of the first k projection. I can write the orthogonal sum that because the projections associated to this band are mutually orthogonal. They belong to part of the spectrum which have no intersection, then are automatically orthogonal. Then this orthogonal sum, this makes sense. Then, more, to each gap, I can associate a projection. Okay, I'm labeling the gap with projection. But this labeling in some sense is somehow abstract, because projection in this case are abstract objects. I would like to label my gaps with some number. It means that I want to associate to some number to this projection. I can do this with the trace, okay? Now, the trace associate to each projection in the sister algebra a number which is in this set. And when theta is irrational with the denominator n, the only possible value of this projection are between 0, 1 over n, 2 over n, up to 1. These are the only possible number. And I know that my trace is faithful. It means that if my projection is strictly bigger than 0, if it's not a trivial projection, or if this integral is bigger than 0, this automatically implies that the projection is not trivial, and this is an if and only if. And because of this, and because the additivity of this integral, the labeling made just with the integral just associate to the sequence of gap, a sequence of increasing number starting from 0, which is the bottom gap which goes from minus infinity to the first point of the spectrum, and 1. This one is just the labeling for the Harper gap, which is the gap which goes from the soup of the spectrum to plus infinity. But you know, this labeling is not particularly interesting. I'm just associating an increasing sequence of number. It's the same things to label this gap just with 1, 2, 3, 4. I mean, I'm not adding any interesting information. I have a second way to label my gaps, and is using the Chern class. Okay? I can associate to each projection an integer which is given by the Chern class. The Chern class of the trivial projection 0 is 0, and the Chern class of the full projection 1 of the identity is 0. And for the other projection, well, something can happen. And I decide to encode the information. I decide to encode the Chern class of my gaps of the projection which label the gaps with colors. This is the way in which I decide to code the colors. And when I do this, the butterfly change in some sense. This is the diagram of the butterfly where the Chern classes are computed. This is 1, this is -1, and okay, the colors are... You see, also the structure of the Chern classes is in some sense fractal. There is a structure in the repetition of this Chern number. This is the Chern number labeling for the gaps of the triangular lattice butterfly. This one is for the ensemble lattice. Okay? Now, you know, the problem is how to compute these Chern classes. If I want to label these phases, how I can do. This theorem, this was part of my PhD thesis. I call this theorem abstract TKNN equation. Essentially tell us this: if I took a projection in the algebra for the gap, for the KF gap of an element F, then the Chern classes can be computed by an equation of this type, where S is an integer. Okay? And if I specialize this formula to this formula is correct even for irrational theta. Okay? This formula it's the result of theorem. I don't have to declare that theta is rational. But when theta is rational, I can do something more. First of all, n times the integral of pk is a number. It's a natural number. And if I multiply by n the left and right part of this equation is of this form. And in particular, for instance, in the case of Harper, in the case of the square lattice, all the gaps are open, then this nk is just equal to k. But anyway, this is a Diophant Diophantine equation. Because this is a Diophantine equation for the Chern class and S, I have a solution. These solutions are infinite number of solutions, but I can solve this Diophantine equation. And this solution becomes unique if I have a condition of this type. If I can bound, for instance, the value of the Chern class, this equation gives me the unique equation. Now, this bound here, which is called Windhoek condition, is not only for the Harper case, for the square lattice case. It's an open problem to know if for other operators that are in the non-commutative torus, a bound of this type exists. But if I have a bound, this equation, which works for every element automatically, give me a way to compute the Chern classes and to color my butterflies. Well, why this very abstract business has some interest in physics? Now, how much time I have? 6 minutes, perfect. Why this abstract argument makes some sense in physics? Because of that, I need to talk about representation. Up to now, everything I said to you is without representation. There are two very relevant representations of the non-commutative torus. The first one is a representation on the Hilbert space small L2 of Z2. And in this case, the representation is just defined by declaring the representation of the generator. You know, U0, it's sending big U0, which indeed is a translation in the first coordinate and the multiplication for a phase which depend on the second coordinate. V0 is represented by a translation in the second coordinate, a multiplication by a phase which just depend on the first coordinate. You can check that the commutation relations are respected. And another important information is that this representation is faithful, which means that the abstract spectrum of any element is equal of the spectrum that I can compute on the Hilbert space of the operator obtained with this operator. This is a notion of isospectrality. And, you know, I can construct the representation of, for instance, the Harper, the abstract Harper element of the non-commutative torus, and this is the type-binding Hofstadter operator. This is an operator which is very well studied in condensed matter, for instance, and is usually the operator which describes the motion of an electron on a lattice, on a square lattice, under the influence of a magnetic field. A perpendicular magnetic field. In this case, theta played the role of this magnetic field. Okay? Physically, this is the model for the motion of an electron in a constant magnetic field perpendicular to the lattice.
Non-interactive.
No, non-interacting. This is a free electron. Well, the name Hofstadter because indeed this is the spectrum that Hofstadter computed in his paper. It was not the spectrum of the abstract operator. He computed the spectrum of this object, but today we know that these are isospectral. There is a second representation, which is a representation in L2 of R. Then it's a one-dimensional representation. This is interesting. And in this case, the generator U is indeed the multiplication by a phase. And the operator V is a translation. Okay? Even this representation is faithful. Again, these imply isospectrality. And in this case, the model for the Hofstadter element is this operator here, which is called the Harper operator. Okay? Now, I have to admit that I was not aware about that, but David suggests me that there is a connection between this operator and the Bethe ansatz. I found several papers of this type. In all these papers, the operator which is considered is indeed the Harper operator that I show you. Well, And I was surprised because there is even the study of the Harper operator on honeycomb lattice, which is indeed the guy who give you the honeycomb butterfly. Why these models are related between them? Which is the relation between these two representations? This is the full operator, which describes the motion of an electron in a periodic potential under the influence of a magnetic field which is perpendicular to the system. And you know, usually the full model is complicated and one pretends to have simple models. And there is a semi-classical adiabatic reduction. I don't want to explain in detail what it is, but in the limit of a very small magnetic field, I have an effective theory which is given by the Hofstadter model. And in the limit of very strong magnetic field, the effective theory is given by the Harper model. In some sense, the Hofstadter and the Harper model are describing the effect of the magnetic field on the motion of an electron in the limit of a very weak and a very strong magnetic field. And this, in some sense, gives some information. Also, the structure of the gap of these two models, in some sense, has to be different because they are describing a very different physics. This is the gap labeling that I showed you before. For essentially, this is the Hofstadter regime for a very weak magnetic field. But if I try to put colors in the Harper model, if I want to compute the Chern classes associated to the gap, the colors are changing. Okay, there is a difference of the color. And this difference indeed is essentially given by the TKNN equation that I showed you before. As I showed you before, in this Diophantine equation, there was a Chern class, which was the Chern class of the Hofstadter butterfly, and a second parameter S, which was the second member of this Diophantine equation. What you can prove that this parameter S indeed is exactly the Chern class associated to the model in the very strong magnetic field. This is a duality between weak and strong magnetic field. And indeed, you can associate the color of this butterfly starting from the colors of this butterfly respecting the Diophantine equation. This is just one example for the third gap when I fix the theta 1/4. I don't want to insist on this, but this is interesting because spectral, just the spectrum does not contain enough information. The two models are completely isospectral, but they show difference in the topology, and this difference is evident in the color. Then what I mean, there is something more in the study of the spectral property of an operator if we realize that the projection indeed are topological object. Okay? The spectrum is just given by the support of this projection, but these projections are vector bundle, are topological, then are encoding some information. What I'm doing here indeed is just to exploiting and exploring indeed the K-theory associated to this projection. This is also physically interesting because these Chern classes indeed physically are associated to the Hall conductivity. It's something that we can measure with the experiment, okay? I can prepare my quantum Hall effect experiment, I can measure the transverse conductivity, and this color give for free the values of this conductivity. What else? This is my last slide. There are some open questions. For instance, the TKNN equation works for every element on the non-commutative torus, but what we don't know is the window of condition for a given element, which allow us to solve the Diophantine equation. The second question, this is a curiosity at this level. It's possible to apply the Bethe answers also for other general elements of the non-commutative torus. In the literature, only the Harper, the Hofstadter, and the honeycomb lattice are discussed. But there is some general extension which works for any given element of in this algebra. And maybe the Bethe answers can, in some sense, help in exploring this window of condition. I don't know. And there is another question. You know, I show you in the, I think the previous slide that there is a connection between Chern classes in the regime of weak magnetic field and strong magnetic field. And is this duality a sort of T-duality? You know, these are open questions. Probably it will remain open for many time because I wasn't able to answer any of these questions. Well, thank you for your patience.